This lesson is all about motion in space, specifically outer space, which sounds like a significant deviation from the things we've been learning about this chapter. However, I promise you that the concepts of universal gravitation and centripetal force that we have been learning about are going to come back and play a role here. With that in mind, our objectives for this section are to list and explain each of Kepler's 3 laws, to solve for orbital period and for orbital speed using the third of Kepler's laws that we'll learn about, and then describe what apparent weightlessness is, how it's different from real weightlessness, and what conditions cause it. All right, let's jump right on in. So, there was an astronomer named Johannes Kepler, and he is credited with giving us the first laws that properly explain the observed motion of the planets. As I'm sure you know from history classes and from other science classes, that there were many scientists who came before him who tried different models of the solar system, all of these things, and they gave reasonable explanations that explained the data that they had, or then later on partially explained the data that they had. But Kepler's laws that he wrote were the first explanation that really well matched all of the given data that they had at his time. So we're going to go over them. There are 3 laws of planetary motion as described by Kepler. His first law is as follows. Each planet travels in an elliptical orbit around the sun, and the sun is at one of the focal points of that ellipse. So prior to Kepler, there were lots of theories about, maybe things are orbiting the Earth. Once we eventually figured out they're not orbiting the Earth, people had them in circular orbits, which they are nearly circular, but they are not circular. So Kepler was one who suggested that they might be elliptical in shape. Objects that only have one focal point for their orbit exhibit perfectly circular orbits. So if you had, this is very similar to circular motion as we have been describing it, right? If you have a point in the center that you're orbiting, there's a force holding you in that orbit, your orbit is going to be perfectly circular. My drawing there, not so much perfectly circular. However, if there are 2 focal points, one here and one here, okay, being attracted to both of these focal points causes that orbit to be more elliptical in shape. So like a squashed circle or an oval. While the 2 focal points that the planets orbit are relatively close together, they are not on top of each other, which means that the orbits are nearly circular, but they are not circular, they are elliptical. Here's a better drawing, okay? This is a way you can model this. If you take 2 sort of thumbtacks and you put them at the 2 focal points, and then you run a string around them and the planet, which is a pencil, you'll notice that the circle or the shape that you circle will be a ellipse. Again, a lot of times in textbooks, you will see the orbits made into these dramatic ellipses where they're very elliptical, and that is not the case. Most of the orbits of the planets are close to circular. They're just slightly elliptical, but they're sort of exaggerated for the sake of textbooks so that it's easier to see what's going on. So easy peasy, there's our first one. That's Kepler's first law. Kepler's second law states that if you have an imaginary line drawn from the sun to any one of the planets, and then you pretend that that line is sweeping out areas, if those areas have equal time intervals, then the actual physical area that they sweep out will be equal. Observe this image that's coming up. You have it on your paper already. Okay, if a planet takes equal time to sweep out each of the highlighted sections, then the area of those sections is the same. Okay, the result of this is that planets travel faster when they are closer to the sun and slower when they are further away. So you can imagine if we're over here, this distance from here to here that this takes is going to be a much larger distance than from here to here. All right. Now the areas, the highlighted blue area, is the same, which means as a result, in order to sweep out the same amount of area, the planet has to travel significantly faster when it's on this side than it does when it is over here. Kepler's third law is that the square of a planet's orbital period, which we use the capital letter T to represent, is proportional to the cube of the average distance between the planet and the sun. So the average distance we represent as a sort of radius for these for their orbits. So we use r, and then it's the cube of that distance. Again, it says average distance because these are ellipses. It's not going to be the same distance at every point in the ellipse. It's not like a circle. Written mathematically, this equation looks like this. T, which is orbital period, squared. Then we have the proportionality symbol in the center, and then r for radius, cubed. This equation can also be written to compare the orbital period and mean distance for two separate objects, so long as they are orbiting the same object. So you could compare any two of the planets that are orbiting the sun. You could compare a satellite that's orbiting the sun and a planet. As long as they're orbiting the same object, they will compare in the following ways. If you take the squares of their orbital period and divide them, that should be equal to the cubes of their radiuses divided. The proportionality constant for this equation depends on the mass of the central object. So depending on what it is that your objects are orbiting, this proportionality constant is going to be different. We are going to solve for the proportionality constant for Earth. Or not for Earth, sorry, for the sun. For our solar system. Recall that in motion around the sun, centripetal force is the force provided by gravity, which means we can take the equations for the force of gravity and centripetal force and we can set them equal to each other. Once we do that, we can solve for tangential velocity. And because we know that speed is equal to distance divided by time, we can take the distance, which is the circumference. So we're going to take 2 pi r over t and square that and put it into our equation in place of velocity tangential. And then we'll isolate for t squared and compare it to Kepler's third law. You can try it, and then I'm going to work it out. Okay, so the first thing we were doing was taking the equations for the force of gravity, which is gravitational constant, mass of one object, mass of the second object. So one of those is the mass of the sun, one of those is the mass of whatever object is orbiting. And then the centripetal force equation, which was just mass of the object that is experiencing this, so mass of the orbiting object, velocity tangential squared divided by the radius. So if we know that in this case, force of gravity and force centripetal are the same, we can set them opposite each other and then go ahead and try to isolate velocity tangential. So we want to get this by itself. Okay? Means both sides are getting multiplied by r. So we're going to see one of these r's disappear. And both sides are going to be divided by mass of the orbiting object. So we're going to cancel this out, and we're going to assume that mass 2 in this case is the mass of the object being orbited, aka the sun. So these things cancel out of here, and we're left with velocity tangential equaling g times m over r. Oh, and this should be squared. Okay. Then we said we're going to take our little equation for the speed, right? We said speed is equal to distance divided by time. And so we have to have the distance, which is 2 pi r. So our velocity tangential is going to be 2 pi r divided by the orbital period, the time it takes, right? So we're going to take our lovely 2 pi r over t, the orbital period, which is our time, and we're going to square it, and we're going to put it into this equation in place of that. So what we should end up with then is 4 pi squared r squared over t squared equals gm over r. It's not a very good r. Okay. Then we want to go ahead and try to isolate or get t squared on its own. So to do that, we're going to multiply both sides by r, and we're going to wind up multiplying both sides by t squared, and dividing both sides by g and m. Well, let's not get ahead of ourselves. Let's see what we end up with here. So the r's cancel, the t's cancel, so we wind up with g m is t squared equals 4 pi squared, and now r is cubed, and then we're going to divide both sides by gm. And the result that we get from all of this is going to be t squared equaling 4 pi squared r cubed over gm. And if we simply put a parenthesis around this portion, leaving the r on the outside, you'll notice there's some similarities between this and Kepler's third law, correct? So this little piece, the piece that makes them proportional here, is our proportionality constant. We've just solved for it. 4 pi squared over gravitational constant times the mass of the sun. With our knowledge of what the proportionality constant is, okay, at least for our solar system, we can rewrite Kepler's third law to look like this, which is what we just did. In this equation, m is the mass of the object being orbited, aka the sun. Okay, the mass of the orbiting object will not have an effect on its orbital period or on its orbital speed, which is why we can ignore it. The new equation can be written in two separate ways, where we are isolating information in order to solve for orbital period and for orbital speed. So when we're solving for orbital period, okay, we have this equation. And when solving for orbital speed, we have this equation. These are going to be the equations that we use to solve problems that involve Kepler's third law. So let's try one. The Magellan was the first planetary spacecraft that was launched from a space shuttle, which is pretty cool. And it went to orbit Venus. During its fifth orbit around Venus, Magellan traveled a mean altitude of 361 kilometers. If its orbit had been circular, what would Magellan's period have been? We're going to use figure 3.3 on page 242 of your textbook because it gives values for both the radius and the mass of Venus, which we're going to need. Go ahead and give this a try. See if you can figure out which equation you need, and then go ahead and solve for it. And go ahead and solve for speed too while you're at it. Do period and speed. All right. So let's start with orbital period. The equation that we're going to want to use is that T equals 2 pi square root of r cubed over g m. So we should have all of this information. We can either look it up or we know it already. Okay? So we can substitute in the information and solve. I'm just going to go ahead and erase this portion and we'll just write it in as the number values. So we have 2 pi, the square root of our radius, which we can look up in the chart and find is 6.41 times 10 to the 6th. And that's meters. And we're going to go ahead and square that. Or not square it, cube it. Already forgetting the equation. And then that's going to be divided by that gravitational constant, our lovely 6.673 times 10 to the negative 11th. And it has that great unit, newtons times meters squared over kilograms squared. And then we're going to take this times 4.87 times 10 to the 24th kilograms. So there's our mass of our object. Object being orbited, which in this case should be Venus. Okay. And then when we run the math out on this, it's a long, complicated math run, but we should discover that it is 5.66 times 10 to the third seconds, because this is a orbital period. Then we can run the next one. So for this one, if we're solving for the speed, tangential speed, we're going to be using velocity tangential is equal to the square root of gravitational constant times mass over radius. So again, we're just going to plug values in, get that gravitational constant. Newtons times meters squared it's supposed to be an N, over kilograms squared. Take that whole thing times the mass that we just had in the previous question. Over the mass, mass over the radius. To the 6th meters. And when we go ahead and do all of that math, we come out with 7.12 times 10 to the 3rd meters per second. So there's your answer for the second half. All right. Let's talk about weight and weightlessness, because this is another thing that we experience that's connected to gravity that's happening out in outer space. In a previous chapter, we learned that weight is really just the magnitude of the force on an object due to gravity. Okay, so if your gravity changes, your weight changes. Scales are actually measuring that downward force that is exerted on them. When your weight is the only force down on a scale, then it reads your true weight. But if your friend were to push down on your shoulders or step on the back of the scale, it would reflect an incorrect weight because it would be receiving more downward force than you are actually experiencing. Newton's third law tells us that this force of gravity, or weight, is equal to the normal force that is acting up on you. Imagine you are standing on a scale in an elevator. When the elevator is at rest, the scale would read your weight, and you would experience all of this weight. Because you would experience both the pull downwards of gravity, but you would be feeling that upward normal force on your body from the floor beneath you, which is what really gives us the sensation of weight. As the elevator begins to accelerate downwards, the normal force on you will be smaller because you are accelerating. Okay, and the floor is accelerating with you. So it's going to record on the scale less than your actual weight. And if by some happenstance the downward acceleration of the elevator matched free fall acceleration, you would have the same acceleration as the elevator and therefore feel no upward normal force from the floor at all, and the scale would read 0. While you still have weight, obviously, the scale reads 0 because there is no normal force acting on you in that situation, because you're in free fall. This phenomenon is what's known as apparent weightlessness, where you are obviously not weightless because there is a force of gravity still actively acting on you, but you feel weightless because the normal force is not acting back up on you and telling you otherwise. Okay? And coincidentally, astronauts that are in orbit around the Earth are experiencing apparent weightlessness. They are still having an attractive force from the Earth. They are not far enough away from the Earth to have lost all of that attraction. But because whatever ship they're in is essentially in orbit, free falling around the Earth, they do not feel any normal force on their body because they are constantly in free fall, and therefore they feel as though they are weightless. In order to experience true weightlessness, you would have to go somewhere in the far depths and reaches of space where you are so far away from any gravitational body that you do not experience any gravitational pull. And that would be what we would call true weightlessness, because in that case, you would not have weight because there is not a force of gravity pulling on you. The weightlessness that we can experience on roller coasters and when we go over hills too fast and for astronauts in outer space, that's all apparent weightlessness. right. That should be the end of our notes.